Welcome to the second lecture for the course of machine learning, and the topic that we are going to cover today is linear regression. So linear regression, as I mentioned earlier, it is a method to determine the relationship between variables, and then we use the relationship between the variables to evaluate the trends in the data, and based on that we make the estimates or forecast on unobserved examples. So the contents for today's presentation will be linear regression, polynomial regression, and additive linear models. So what is the goal of linear regression? We have to find the line that best fits the data, or in another word, in a line which generalizes the given data. Here we can see the blue dots. For example, on the x-axis we have the age, and on the y-axis we have shoe sizes, age in years, shoe sizes in millimeters. So x and y, they form a pair. For a given age, we record shoe sizes of different people to form this data set. In this, the xi, because we have only one variable on the x-axis, it is univariate, so x is your predictor variable and y is your predicted value. You can also represent it with y hat. And we used all the data points in the data to determine this black dotted line, which is your function f of x. And this function generalizes the trend in your data. So what is the trend that we are observing in this data that this black dotted line is trying to represent? It's representing. It represents that as the age of a person increases, the shoe size in general also increases, although there can be some discrepancies, or we can say not all values would change linearly, but this linear line will represent the general trend. So this is the target of your linear regression. Here we call x the independent variable and your y is the dependent variable, because your y depends on values of x, which are the predictor variables. For this given example, we have only one variable on the x-axis, so our equation can be represented in this format, that we are familiar with, where c is your intercept and m is your slope. Now we will study what is the slope and what is the intercept in equation of a line. Intercept is the value of y at which the value of x is 0 here. So this point will be your intercept. The value of y where x is 0 in the case of this equation, y is equal to mx plus c. This will be your intercept. Sorry, c will be your intercept and m will be your slope. Now let's talk about the slope. What is the slope? Slope is defined as the increase in the value of y at these 2 points. What is the increase in the value of y, delta y, which is y2 minus y1? Put it simply, what is the increase in y for a unit increase in x? So this is x2, this is x1 for example. Then the slope will be defined by delta y by delta x, slope m. This is for the case of a single variable. Slope is defined as the change in y for a unit increase, one step increase of your x. So not all your real life situations are univariate. Here we have like age increases and we see there is a trend that shoe size also increase, but there could be several other factors that could determine the shoe size. What are the other variables that can affect the shoe size of a person? One is age. One is gender. Can gender affect or does gender affect the shoe size as the person ages? And what is the relationship between the gender and the shoe size when the person is growing up? So this is another variable G that could be involved, that could influence the shoe size of a person. So in that case, we would have multiple variables. And we call that the multiple regression. Here, this W0 will be your intercept, and the effect because of variable x1, for example age, variable x2, the effect of gender, and some other variable may also be involved. So what is the effect of this variable provided the other variables are kept constant? Then we evaluate the next variable, the other variables are kept constant. So in this multiple regression, we study the effect of different variables, predictor variables, to estimate the trend in our data. So your basic equation where we started with one variable, we rewrite this equation as f of x b0 plus b1 x. So we can see here that this is your W0, and okay, we replace this with W. So this is your C is now become represented as W0 and M is represented as W1. So this is for one variable, and then when we increase the number of variables to multiple, regression or equation will appear in this format: W0, first variable, second variable, and third variable. So now if we want to represent this equation, it can also be represented that W0 does not have a x term with this, but all the rest of them have the x term. So we can represent it W0 plus, start from j is 1, w is 1, x is 1, up to d. That means we have total d variables. So if we have d variables, what we will do is we will sum up wj, xj starting from 1 to d, and then we will add the intercept. Remember this equation because this is what we will use in the whole rest of the lecture. So now we have n sample data where d is our data set, where each d subscript I represents a data set that is represented as a pair of xi and yi. Xi is the predictor, yi is the expected value or the predicted value. Most commonly we use the expected value. So xi and yi. The data is represented in this form, where your data, the variable can range from 1 to d, where this is used as an input, d-dimensional input space, and yi is the output of xi. The output, expected value, then the predicted value, these are some of the representation of your y. So now what we want to do is we want to find a line that best fits the data. We call this best fit. So what is best fit? Which line would best fit this data? How do we know this line is the best fit for these data points, these blue data points? One way of doing that is that we minimize the error. We make f of xi as much as possible close to yi for all the data points up to n. So starting from 1 to n, we minimize this error or loss absolute value of the difference between what we have calculated, f of xi, and the original yi. So here if you look at this line, what is f of xi minus yi in this line? This is the difference between each data point and the f of xi, line f of xi, which is the line that represents the trend of this data. And we call this the residual. It will have a numerical value that can be positive or negative. For example, if this value is higher, then it will be positive, and if this value is lower, then this value will be negative. So direction of your residual or your error, at this point this residual will have a positive value, but in this the original data is larger and your trend line or f of x is smaller, so your residual will be negative. So what we do is we don't consider the in the magnitude representation, or we call this the absolute error, where we are considering only the magnitude of the error in a set of predictions without considering their direction. And the mean absolute error we define as it is the average over the test samples of the absolute difference between predictor and actual observation when all individual differences have equal weight. In other words, we can write it, we have to find these W's. We also call them the regression coefficients. We have to minimize this and find our W's. One representation is this. So find your W's given you have this equation such that it minimizes the error, where f of xi can be represented like this. So as I mentioned, we can represent it in this format. So we are trying to minimize this distance between the actual and the estimated f of x. In other words, we find the W that minimizes not only the absolute error but also the, here it is a squared term, squared error. So what is the squared error? It is the average of squared difference between prediction and the actual observation. So if we have divided by n samples, then it becomes the mean squared error. It takes the squared difference between the predicted and the actual observation. And so our problem now becomes we have to choose which of the equation or which of the method is more suitable. Either we consider the absolute error or should we consider the squared error for our problem. To minimize the gap, these residuals, we have to minimize the residuals between all the data points. So now the representation can be stated as find the W's which minimize the squared error, where your f of x is represented like this, the rotation is this, where D is actually a set of points xi, yi. Now let's have a brief discussion on the absolute error and the squared error. We know that these are negatively score oriented, means the smaller the value, the better it is. Both of them, the smaller they are, the better it is. So now what will be the effect of choosing either of them? The mean squared error does not necessarily increase with the variance of the error. This is an important point. It increases with the variance in frequency distribution of the error magnitude. So we can use the squared error when large errors are undesirable. Here is an example. In the first case, we have evenly distributed errors. We can see here, this is our sample number and this is the error estimate. The second column is the error estimate. Third is the magnitude or absolute error, and the third one is the squared error. We can see that the mean of all these errors is 2 for absolute error, and for the squared error it is the same, 2. So now we consider the same example, another example which has a small variance. So the error is 1 and 3. So these two values which have a slight variation, here we did not have in the first example any variation, but now we have some variance in the error. So the magnitude error is 1 and 3 and the squared error shows a difference between the magnitude and squared error compared to the previous estimated. The mean absolute error in this case also remains the same, but the root mean squared error changes, so it is sensitive to variation in the magnitude of your errors. In the last case, we have a large outlier. So initially all the errors were 0, but the last entry had an error of 20, absolute of 20, and the error squared was 400. So we can see the absolute error in the 3 examples cases, it remained 2. But it had a large effect on the squared error term when the variance in your error distribution changes. So squared errors are suitable when we want to avoid large errors. Now our target will be to train an algorithm that reduces this squared error. And in this problem, if we were to choose based on the absolute error, so the absolute error for the 3 cases is the same, so it cannot be interpreted that well. But if we choose the squared error, we can have a good interpretation of all results and train the model accordingly. So now we choose the squared error as a loss function to find the values of w's for a given f of x. So there are different ways to solve it. We will choose the simplest one in this lecture. So it is clear what is the point at which your e of w is minimized. It is clear it will be when the derivative of your function e is equal to 0, where j is from 0 to d. For all the values of w's, wj means w1, w0, w1, w2, w3. So we take the derivative, w1, w2, all of them should be equal to 0. So it can also be represented in this form. So we are taking the partial of f of x I, which is the same, minus yi squared, and it can be represented in this form. So for our value of j is 0, we can see here in the first term we don't have a multiplier xi, but in the next terms from 1 onwards, from I is 1 to I is equal to d, we have a multiplier x term. So when j is greater than or equal to 1, we have a multiplier term xij. So this is the partial of this loss function. 2 of f of xi by I when j is 0, and 2 of xij multiplier term f of xi minus yi when j is greater than or equal to 1. So in other words, that equation can also be represented in this form. Each equation can be represented separately, starting from x1 to xd, and then for first intercept term when j is 0, in this case when I is 0, it will also be represented like this. So if they are d variables, xi, they are d variables, then we have d equations. And we solve this equation to find our w0 to wd. So our data can be represented in the form of equations. So the first equation, we have this for j0. It can be represented like this. Where did this term come from? It comes from here, w0. For the first one, we determined that this f of xi minus yi was equal to 0. So minus yi equal to sorry for the bad handwriting. So this f of xi minus yi, this is from where it comes from, so we can represent it for j0. The first equation can be written like this, is equal to 0, and then for the next term we have always the multiplier term. So we have, if d variables means x can go up to d, so from x1 to xd, so we will have d equations. Again, rewriting this equation, we can apply the summation separately to each of them, and then we have yi, which goes here on the right hand side. So we have a representation of our problem in the form of equations. We can represent them. So if the problem can be represented in the form of an equation, we are aware system of equations can be represented and solved using matrices. And we have studied matrices and their inverses. So in this case, we have a of w, which is minus b, should be equal to b. So w is our w naughts, b is our y's, and a is the matrix that we represented like this. W naught 1 xi xd, we can see here 1 w naught, then xi w1. So this can be represented in this format. And then if we want to find the value of our w's, what do we call the w's? Regression coefficients. We want to find the regression coefficients. So here we can see in this equation, these two or the rest of them have a pattern where the first term is this x of I 1, then it is multiplied with all the terms in that row, and if it is x of d, then it is multiplied to all the terms. But in the first row we can see we don't have such multiplier, we have only 1. We have a 1 which is used as a multiplier, 1 multiplied by, we can write it like this. So another way we can represent it is if we replace x of I naught with 1. So we can start our summation equation from 0, where the variables will be, predictors will be starting from 1, or xi naught equals to 1. So I hope you understand where are we going with this. So this multiplier term, as I mentioned earlier, 1 is replaced with xi naught. Why? Because we want to start the summation from 0. We started the summation from 0, and then the general representation can be in this format. Now we can rewrite this. So now our matrix has a general form. It can be represented in the general form. We can see we have one equation for w naught, and then we have d variables and d equations. And since we are starting from j naught, so here on the right hand side, for the first term we will have x of y naught, which is a multiplier here, and then from x1 to xd. This can be represented in the form of a matrix. So I heard in the online lecture that there was some confusion, so I want to clear this. We want to represent our matrix A in a generalized form. So generalized form here in this case, we know the conditions for our matrix and its inverse. So our A matrix is of the form n cross n, size n cross n, and there are some conditions to find if the inverse of a matrix exists such that A inverse A or A inverse A should be equal to identity matrix, and that the determinant of this A should not be equal to 0. In this case, we can find the A inverse to find the value of our regression coefficients or W. What about if we have a generalized matrix? The first term is for W0 and the rest are 1 to D, W1 to WD for D variables. So what about if our matrix X is of the form M cross N? Then how do we find the inverse? So the generalized inverse can be found for all types of matrices provided that the determinant of the matrix X, why don't we represent it with A? Okay, or this matrix A should not be equal to 0, and the other condition is that AGA should be equal to A. So what is G? So now our G is the generalized inverse of this matrix A. And how we can do that, how we can achieve that? It is by this X transpose multiplied by A. So we can represent our matrix G, which is the inverse of A, in this form. So now if we want to prove that G is definitely the inverse of matrix A, of a generalized matrix of the form M cross N, then it should satisfy these two conditions. First conditions, then your AGA should be equal to A, and the determinant of this A should not be equal to 0. Following on this, so this is another notation for finding the inverse of a generalized matrix.